Okay, so looking at lipids, right? So we've finished carbohydrates. Now we're talking about lipids. So lipids, these are a class of biological molecules which carry out multiple functions. For instance, we've got body fat, right, which is important for energy storage. That's why you see when someone is not eating well, you say, "Oh, okay, this person is losing weight." Why? Because when we've got excess glucose, right, it can be converted to fat, and that you say, oh, someone has started gaining weight. And then the other important thing is about heat insulation. That's why you might hear, oh, people that are a little bit maybe have got more weight, you'd find that they are better insulated against heat loss, isn't it? And then the other important and the largest function of lipids in cells is the fact that they are used in the formation of cell membranes, and we'll dwell on that in a short while. Now, the other thing about some lipid functions is that there are also some vitamins such as vitamin E, vitamin A, D, K. Those are lipid soluble, right? So they dissolve in lipids. But then such as some vitamins such as vitamin E are very, very important as well. And then a lot of lipids also form what we call steroid hormones. So steroid hormones are very, very important because these are hormones that actually determine whether someone looks like a man, whether someone looks like a female. I'm sure you've heard of hormones such as testosterone, but those are things that you discuss in your physiology and biochemistry. Now, remember, we talked about carbohydrates, right? And we said carbohydrates had monosaccharides, disaccharides, and polysaccharides, oligosaccharides. But for lipids, lipids are a little bit interesting because lipids are not like polysaccharides. In short, lipids are not polymers. Okay, lipids are not polymers. Lipids are just small molecules that have strong dependence to associate through non-covalent forces. So usually most people get this question wrong because how they will ask it is they ask which of the following is not a polymer, and there will be lipids there, and people will write all sorts of answers, but the correct answer is what? Lipids. Lipids are not polymers. Okay, now lipids are usually characterized by a kind of structure shown in figure 1 below. So when you look at this structure, this is what we call the general structure of what? The general structure of lipids. So what are you going to see? You're going to see a polar head group. So remember from our introduction, we talked about what polarity means, right? So this is something that is going to be hydrophilic, meaning that it's water loving, meaning that it's going to what? To dissolve in water. So it's going to have a polar head group, which is hydrophilic, of course. Then and that's the one that's going to have, okay, yeah, we've seen the carbonyl group and the hydroxide. Then this hydrophobic part, this is, or the non-polar part, this is, you can see, that's the carbon chain, right? You call it the carbon chain or the backbone chain. Now when you see there are no hydroxides, there are no carbonyl groups, so that is just going to be what? Hydrophobic. In short, it doesn't love water, it won't dissolve in water, right? Now this structure is very, very important, and because of the nature of lipids, the fact that they've got a hydrophilic part and a hydrophobic part, they actually are called a very interesting name. They are called amphipathic, right? So you can just see that spelling there down. So amphipathic, right? So amphipathic, it comes from the word amphibian, right? And what's interesting about an amphibian is that it can live both on land and in water, isn't it? So the same thing, that's where the amphi comes from. So the antipathic, this means the molecule has both a hydrophilic part and a hydrophilic part. Oh, sorry, hydrophobic part. So it has got both a hydrophilic and a hydrophobic part. And so this is what makes lipids to be very, very interesting. And you see how these same principles, interesting features allow it to actually be able to be used in the formation of what? In the formation of cell membranes. So here, this figure, what it's showing you is showing you three ways in which lipids can actually arrange themselves when they are exposed to water. So remember, we talked about the fact that they are going to have a hydrophilic part and they're also going to have the hydrophobic part. Now, what this basically means is, let's look at the first part. So look at the first layer. So the first layer, you are getting what we call what? A monolayer. So with that monolayer, that's what happens when we attempt lipids in water. Now, remember I said that they will form one or more of the structures shown. So we've got a monolayer, a micelle, and a bilayer vesicle. So for the monolayer, that's what happens when, okay, when they are placed on the water surface with the head group immersed. So what this basically means is, when I get lipids and then I put their polar head, remember we saw the polar heads, right? When I place the polar heads on water, the lipids will orient themselves so much that the hydrophilic polar heads will be towards the water. Then as you can see those tails, right? The hydrophobic tails, they will be arranged away from the water. So because they are arranged away from the water, you see that it forms some sort of a layer. It's called a monolayer. It's just one layer. But the important thing is that the polar heads, and they would actually like asking this in the exams. So the polar head is hydrophilic. What does hydrophilic means? It means that it loves water. It loves to interact with water. So that's why the polar head is the one that's going to be in contact with the water, whereas the tails, right? Those are the ones which are going to be away from the water, because as we explained earlier on, those are what? Those are hydrophobic. Now, for instance, for one reason or the other, we shake this beaker or whatever it can be vigorously, right? Or we stir the water vigorously. Now, this is where we can now have either a micelle or we actually have a bilayer vesicle. So what's going to happen for a micelle is that it's going to be a spherical structure. So what happens in a micelle is those polar heads, they are going to be outside and then they'll arrange themselves in such a manner that the hydrophobic parts are going to be in the middle. Okay, so they're going to be on the middle. You can see how that micelle is arranged. So you see that those hydrophobic parts are actually on the middle, because remember the key thing is that those parts are hydrophobic. They don't want to be in contact with what? With water. So because they want to be in contact with water, that's why the arrangement is so much that those parts are more or less like hidden from the water. Makes sense, right? So, and then the polar heads are the ones which are outside. Now, the bilayer vesicle. This is interesting because what you're having here is, it's remember, look at how the monolayer was and look at how the bilayer. So for this one, it's not that the hydrophobic parts are at the center alone. What's happening is that you've got an outside layer which has got the polar heads facing the water, and then you've got the hydrophobic parts which are inside. However, in that very inside, you also find that the polar heads are actually in the middle, and they're also projecting their what? They're also projecting their hydrophobic parts, so much that you are getting two layers of polar heads. So you can see those hydrophilic polar heads, and then in the middle of those, you can see those hydrophobic tails which are interacting. So that's what you call the bilayer vesicle. As a result, lipids are defined by low solubility in water and high solubility in non-polar or organic solvents such as chloroform or benzene. That makes sense, right? Things like cooking oil, they struggle to dissolve in water, isn't it? So those are important things to take note of. Now, this bilayer is very, very important because actually that's how our cell membranes are actually made up, or rather that's the arrangement that our cell membranes actually have. So that's a very, very important concept to be comfortable with. So that's a bilayer vesicle. So they ask you which arrangement of lipids makes up the cell membrane. It's the what? the bilayer vesicle. Okay, which is one of the three forms in which lipids can orient themselves when they are in contact with water. But when they are dipped in water, they can't have a monolayer. The monolayer is just when they are exposed to the surface of water. But a micelle and a bilayer vesicle, those are the arrangements when they are dipped in water. So lipids can be classified into two classes. So they are going to be the simple lipids and complex lipids. So simple lipids rather, these are lipids which contain carbon, hydrogen, and oxygen, pretty much like the carbohydrates, right? Remember that carbohydrates only contain carbon, hydrogen, and oxygen, right? So the most common are fats, a combination of glycerol and fatty acids that are solid at room temperature. So remember, glycerol is an alcohol, right? So glycerol is an alcohol, and then fatty acids are acids, of course. So we'll look at how they interact in a short while. So those are simple lipids, right? So they'll just have carbon, hydrogen, and oxygen, and nothing else. The most common being fats, which are actually formed from the interaction of glycerol, which is an alcohol, and fatty acids. And these fats are going to be solid at room temperature. So complex lipids. So complex lipids, these are a little bit more interesting because they have fatty acids quite alright. They have glycerol quite alright. But then they also have two other parts. They'll have the phosphate and polar molecules or the choline group. So these are complex, right? So they are not your normal lipids. They've got a phosphate group. The phosphate group is the PO4. We discussed it when we were looking at radicals in chemistry. So mm, those are the things that you want to know. So know these four active ingredients, very, very important. You can just be asked which of the following uh, four ingredients are contained in complex lipids. Remember, your exams are multiple choice, so they can ask anything. And remember, when you get something wrong, they subtract marks. That's why they always put an option for I don't know. So that's the thing there. So know those parts. So fatty acids. So let's now talk about fatty acids because here we now want to go deeper into the concepts of these lipids. So let's start with fatty acids. So what do we know about fatty acids? Fatty acids are carboxylic acids. In other words, what carboxylic acids? You see that carbonyl group, the carbon atom that's double bonded to oxygen and then to the hydroxide. In short, uh, fatty acids are carboxylic acids, which means the function group is COOH. Okay, so that's important to take note of. Now, for these fatty acids, we're actually going to have two broad types of what? Of fatty acids. There is the saturated and the what? Unsaturated fatty acids. Now, what determines whether a fatty acid is going to be called saturated or unsaturated? It all depends on the carbon chain. So it's not determined by the function group. The function group is going to be the same since they are all carboxylic acids, right? But where the difference is going to come from, the difference is going to come from the backbone, the what can I say, the hydrocarbon backbone, right? This carbon backbone, which has got the carbons, the hydrogen, carbon, hydrogen, that's what's going to determine whether something is a what is a saturated or an unsaturated fatty acid. So what is an unsaturated fatty acid? So a saturated fatty acid, this is a fatty acid that does not contain double bonds. So saturated fatty acid, this is where the carbon chain or the carbon backbone doesn't contain any double bonds. It only has single bonds. Whereas unsaturated, of course, it can have one or more double bonds in its what's this in its backbone. Now take note, I don't mean this double bond that is this carbon that's attached to the to the oxygen by a double bond. No, I don't mean. I mean a double bond between any two carbon atoms. That's what I mean. So, like you see here, you see this diagram, right? Between carbon 4 and 5. Yeah, that's the kind of double bond that I'm talking about. Now, whether something is a saturated fatty acid or unsaturated acid, that actually affects the empirical formula. So remember in chemistry we talked about the empirical formula, and also when we are looking at carbohydrates, monosaccharides, disaccharides, we talked about the empirical formula. Now, how they'll ask these questions is they'll just tell you uh, uh, this is a saturated fatty acid with 8 carbon atoms. Which of the following is the empirical formula? That's how they'll ask you. So what you need to know is that for a saturated fatty acid, empirical formula is going to be CnH2nO2. So what does that mean? That N is for the number of what? Number of carbon atoms. N is for the number of carbon atoms. So if they tell you to say we are looking at a saturated fatty acid which has got 8 carbon atoms. So you see in that empirical formula, CnH2nO2, what do? You just put 8. So as to be C8, 2 times N, that's going to be 16 O2. Now, so it's going to be C8, H16, O2. Now, since you know the share, the structure of this, since you can break it down, you can actually be able to realize, say, oh, actually, I know that those two oxygens are for the carboxylic acid part, and I know that one carbon from the 8 is for the functional group, and then one hydrogen is also for the functional group. So you see that when you get the carbon, you take it to the functional group COO, and then you also get one H to the functional group, you put it at the end. You see that it looks more like a carboxylic acid, isn't it? So these are things that you should be comfortable with. So you should know the empirical formula of a saturated fatty acid. So can someone tell me what is the empirical formula for a saturated fatty acid which has 9 carbon atoms? Which has 9 carbon atoms. 9 carbon atoms. What is it going to be? What is it going to be? So yeah, you can go through that. Okay, so now let's now talk about unsaturated as well. So for the unsaturated fatty acid, again, the empirical formula. Now here, this is interesting because for the unsaturated fatty acid, since those double bonds can be many, it can be 1, 2, 3 different numbers, right? So because of this, the empirical formula is going to be different depending on the number of double bonds that the particular fatty acid has. So for instance, for this one, empirical formula for an unsaturated fatty acid with one double bond is going to be what? CnH2n minus 2 O2. Now, so that you don't memorize, why is the negative 2 there? So the negative 2 is coming into form, okay? It's coming into form because when you put a double bond, already you've taken 2 places for the hydrogen atoms, okay? That's what it means. So that's why here they're subtracting 2 hydrogen atoms, because when you put a double bond, you are actually taking 2 places where the hydrogen atoms were supposed to be. And then where there is a double bond, there's going to be a kick, there's going to be a bend in the structure. So look at the saturated fatty acid, it looks straight here, right? It looks all straightened up. But then when you look at the unsaturated one, it's got a kink, it's got a bend there. So a double bond in the hydrocarbon tail introduces a kink as shown in the previous page. In figure A, the empirical formula for saturated, I've already talked about that. Okay, so yeah. However, there's an extra hydrogen bonded with carbon 7 at the very tail of the fatty acid. As a result, an example of the empirical formula of a fatty acid is that and not that. So there again, just trying to explain that same concept that I had alluded to. Now remember, I mentioned that for the empirical formula for the unsaturated fatty acids are going to be different depending on the what? Depending on the number of double bonds. So if you've got one double bond, it's going to be CnH2n minus 2, isn't it? But when you've got two double bonds, that means you are getting rid of, or you are, remember, one double bond removes two hydrogen atoms, two double bonds removes four, three double bonds removes six, four double bonds removes eight hydrogen atoms. So that's why you see those numbers 4, 6, 8. So that's the way to remember them so that you don't memorize a lot of things. So the simplest lipids are the fatty acids, which are also constituents of many more complex lipids. A fatty acid is composed of a long hydrocarbon chain, which is a tail, and a terminal carboxylic head, which is the one that's going to be hydrophilic, the head. The carboxyl group is ionized normally under physiological conditions. So let me just explain what this means. So what they mean is this is the carboxylic part, right? For the acid. So when they say it's ionized, meaning it's existing like this under physiological parts, right? So it's got a negative part or what you call a basic part, and then it can also interact with what we call acidic parts, right? So because it can, again, we'll discuss this when we look at acids and bases in chemistry. So the fact that it's able to produce a hydrogen ion or what you call a proton, that's what makes these fatty acids to be what? Acidic. So that's the concept there. That's what they're trying to explain. So the carboxyl group, gives fatty acids the acidic properties I've already explained there. So the long hydrocarbon chain is uncharged, right? Since it's just carbon, hydrogen, carbon, hydrogen, carbon, and hydrogen, it can't be charged. It's not charged. It's non-polar. Okay, fatty acids occur in large amounts in cells, but rarely in a free and complex state. So in short, they are saying these fatty acids, they exist in large amounts in cells, but whenever they occur, okay, when they occur, they rarely occur in a free state. So it's rare to find a fatty acid just alone, because remember, acids are very reactive. You get sulfuric acid, you throw it on the floor, it will be foaming and everything, right? So it's trying to react with anything that it can find on the floor. So the same thing for fatty acids, right? So because of this, they are going to react with what? With glycerol. Glycerol is an alcohol. So when a fatty acid, which is a carboxylic acid, reacts with an alcohol, that forms a what? An ester, okay? Or an ester, so as some people can call it. And that process is called what? Esterification, okay? So that's very important to take note of. Most of the fatty acids found in nature have an even number of carbon atoms. Again, that's an important point that you should know. Most of the fatty acids found in nature have an even number of fatty acids. And as you saw there, it makes sense. Yeah, that they should have an even number. Because remember, one carbon, rather one hydrogen will have to go to the carboxylic end and everything. So yeah, remember that. Certain marine organisms, however, contain substantial amounts of fatty acids with odd numbers of carbon atoms. Fatty acids are either saturated, where all carbon to carbon chains are single bonds, or they can be unsaturated as we've discussed. So if a fatty acid has a single double bond, it's said to be monounsaturated. Okay, so you look at a fatty acid and it only has one double bond. So it only has one double bond, then it's called a what? Monounsaturated. But when you look at if it has more than one double bond, then you call it a what? You call it uh, polyunsaturated. So basically, that's how you want to understand these things. Okay, so common, the two common fatty acids are stearic acid, and they've given you the formula there. Very, very important to know stearic acid. Very, very important. Perhaps you may have seen it on a number of items and things like that. So very, very important for you to know stearic acid. And then the other one is oleic acid. Yeah? So again, for oleic acid, you can see that formula. So the difference between stearic and oleic acid is the presence of one double bond in the hydrocarbon chain. So just by looking at their structures, you can already figure out which one has got a double bond. So the one that has got fewer hydrogen atoms, that's the one that has got a double bond. And you see there it's just what? Subtracting what? Subtracting uh, two hydrogen atoms because there is a what? Because there is a double bond. So basically that's the understanding that you need to have. Okay, so answer, yeah, so that's that. As can be seen in figure, a kink introduced by a double bond makes the structure bend. So I already talked about the fact that a double bond is going to introduce a bend in the structure of the fatty acid. Unsaturated fatty acids are slightly more abundant. And let me just check. I didn't miss anything just to be sure. Okay, we're in good shape. So unsaturated fatty acids are slightly more abundant in nature than saturated fatty acids. Okay. The most common unsaturated fatty acid is oleic acid, which we've talked about, which has got one double bond between carbon 9 and 10. If you can remember that, please do remember that. The number of double bonds in an unsaturated fatty acid varies from 1 to 4. But in the fatty acids found in bacteria, this number rarely exceeds 1. So the empirical formula for a saturated fatty acids, one with no double bonds, we've talked about these things. Huh? So it's a little bit more like repetition. Yeah, we've talked about if it's got one double bond, it's minus 2, two double bonds, it's minus 4, three double bonds, it's 6, four double bonds, it's we said 8, isn't it? Okay, so you see there that what's interesting here is you see that the saturated ones, you see that the saturated ones, um, they actually tend to have higher melting points. Okay, so you can see the first one and the third one, they've got the same number of carbon atoms. They've got the same number of carbon atoms, the first and the third one. But you can see just from the number of hydrogen atoms that the first one has two hydrogen atoms more than the third one. So that means the third one, since the difference is just two in hydrogen atoms, meaning it's got one double bond, isn't it? So again, it makes now look at the difference in the melting points. The one with the double bond is -5 degrees Celsius melting point, whereas the one with which is saturated without a double bond is what? 13.4 degrees Celsius. So again, that tells you something about that. Again, look at the second one, that's unsaturated. You see 86 melting point. So you'd expect that to be a solid at room temperature. Look at 4. 4 is 16, 16 again. That's 32. So again, that's saturated as well. Look at just how high they are. Okay, so long hydrocarbon chains of fatty acids are extraordinary efficient energy storage. So now this is very, very important because when you look at long hydrocarbon chains of fatty acids, they are extraordinary efficient in terms of energy storage because they contain carbon in fully reduced form and will therefore yield a maximum amount of energy on oxidation. They are in fact much more efficient energy stores than carbohydrates. For this reason, lipids are used by many organisms, including humans, for energy storage. So here, what they're just trying to say is that when you look at how the carbohydrates are, you will realize that carbohydrates usually have hydroxides, right? So the fact that they've got hydroxides in their structure means that there is already some extent of oxidation, in the carbohydrates. But when you look at lipids, they've got long chains of what? Just carbon, hydrogen, which are in their fully reduced form, especially when you talk about the unsaturated ones, right? In their fully reduced forms. And so, meaning that oxidation can go on and on and on and on. That's why lipids produce a lot of energy more than carbohydrates. A lot of energy more than what? Carbohydrates. That's why animals, humans alike, have evolved to convert what? A lot of excess energy into fat. Okay, because they know that when you convert it to fat, you can store a lot of energy in fat as compared to carbohydrates. So that's what those notes are trying to explain. Now let's talk about triglycerides. So a triglyceride, by the name, when you hear tri, you're talking about three glycerides. Just this is what is formed when a glycerol molecule interacts with three fatty acids. Okay, so how does it happen? It occurs in three steps, right? So you see triglycerides, meaning you are going to have three fatty acids, right? So the first step is going to be look at the interaction. So the structure on the left, the one on the far left, that's the structure for glycerol. You can see it's an alcohol there, or you can call it a trial because it's got three hydroxyl groups. Then that hydroxyl groups interacts with what? With the hydrogen uh, from the what? From the carboxylic part of the fatty acids. Because remember, like what I said, so this is what happens. You see, this part, this part can break off, right? And this positive hydrogen can then interact with what? With that hydroxyl from the alcohol to form what? To form water. Okay, so that's how it happens. Okay, so it's that particular hydrogen there that I talked about on the carboxylic group is the one that's going to interact. So you see the interaction there, of course, water is going to be formed and then that bond has been formed. And as you can see, that's that's an ester because you want to remember that an ester or an ester, depending how you pronounce it, an ester will always be like this. So remember that's how an ester is going to be. And that's basically how that particular structure is. So that's an ester. Now, so we've got glycerol and one fatty acid, they form the bond, and this now the product on the far right is called monoglyceride. Okay, again, since there are other hydroxyl groups, again fatty acid goes there, again interacts, that's going to be glyceride because now there are two fatty acids, and then the third one again goes, then that now becomes what? Triglyceride, which is solid. So fatty acids will react with glycerol to form glycerides. Okay, so glycerol is a simple three-carbon molecule, the hydroxy group on each carbon. So that was the structure that I was telling you there. And so when these interact, the hydroxyl groups, which are the OH groups, will react with the carbonyl groups, which is the COOH of the fatty acids that I was showing you. The bond that's going to be formed is an ester bond. Remember I said it's esterification, isn't it? So remember they'll ask you what bond is formed between fatty acids and glycerol, an ester bond. Okay, each of the hydroxyl group on the glycerol molecule can react with the carbonyl group. So basically it's saying if one fatty acid reacts with the glycerol, it forms a monoglyceride. If two react, diglyceride. If three reacts, it's what? A triglyceride is formed. Okay, so if all three hydroxyl groups of the glycerol react with the carbonyl groups of fatty acids, you form a what? A triglyceride. So uh, glycerides are also called glyceroids. Lipids are substances that are solid in organic solvents such as ethanol, but insoluble in water. So remember, like dissolves like. So organic solvents are non-polar, lipids are non-polar. So therefore, now again, this is something that I want to say carefully. Remember, you heard me talk about the fact that lipids are going to have a polar head and they're going to have a non-polar tail. Now, because the non-polar tails tend to be very, very long, they tend to more or less overshadow the polar head because the polar head is small and the bulk of the molecules what is non-polar. So eventually lipids are going to what to be non-polar. Okay, so just in case you were wondering to say, oh, but it's with a polar head, but how come it's not dissolving in water? So that is one of the explanations. Yeah, so because of that, lipids are going to be insoluble in what? In water, but they're going to be soluble in what? In ethanol. That's why when people are trying to melt candle wax and what, they usually use paraffin, isn't it? Yeah, and then but when you get cooking oil, want to mix with water, that doesn't occur. So that's something that's important to take note of. So basically, that's a structure there that's being shown for a triglyceride. You can see there, R that's just been shortened so that it doesn't look clustered. So storage of fatty acids in organisms is largely triglycerides. I've already explained this is because of the fact that fats are able to store more energy than carbohydrates. Okay, so storage of fatty acids in organisms is largely in triglyceride or fats. These substances are triesters. So triesters basically means that glycerol has reacted with what? Three fatty acid molecules, isn't it? As shown above there. So the general formula of triglycerides is the one shown in figure 2. As you can see there, all the three hydroxides of the glycerol have interacted with fatty acids, and so they form a what? A triester. Meaning there are three ester bonds in the molecule. So the general formula of triglycerides is shown again, it's shown there. Okay, so these, fatty acids can either be the same or different ones. Okay, so that's something to take note of. Okay, so now I believe you recall that I explained something where I said, or rather, I showed you a table which was showing the different melting points for saturated fatty acids, unsaturated fatty acids, And I mentioned to say saturated fatty acids tend to have higher melting points than unsaturated fatty acids. So look at now what we have. We've got triglycerides, which one on the left is made up of saturated fatty acids, and then you've got the one on the right, which is made up of unsaturated fatty acid. So you realize that the one on the left, it's made up of saturated fatty acids, and because they don't have a kink, because they don't have a bend in their structure of the fatty acids, they're able to pack closely together. In short, they're able to you know, to be close to one another. And so because of that, they can be solid. Okay, so that's why triesters of saturated fatty acids are most likely to be what? Most likely to be solid, whereas those of unsaturated fatty acids are most likely to be liquids because of that or those kinks or the bends that they have, and so they can't really interact well and be packed well. So that's something that's important. So most triglycerides, however, contain a mixture of fatty acids which often include unsaturated ones. So fat levels in fatty acids such as olive oil um, liquid at room temperature, whereas those with a high content like butter are solid. Okay, so a wholly saturated fatty acid is a quite firm solid, especially if the hydrocarbon chain is long. And again, like I mentioned, this is because of the high melting points that I showed you for the saturated fatty acids. Okay, and this is because those long saturated fatty acids can pack closely together to form a vascular semi-crystalline structure. And as a result of this, making it easy for them to pack and therefore be solid. Yeah? So that's an important point to take note of. As a result, partial hydrocarbon of unsaturated fatty acid oil like corn oil is used to commercially convert them to solid fat, which can be used as butter substitutes like oil margarine. Now, again, it's very important because there is a process where you can actually convert the unsaturated fatty acids to saturated fatty acids, and then you have a lipid which was supposed to be liquid is going to become solid, and that's where you get all these commercial margarine and all those things being formed. Okay, now I mentioned something about phospholipids, isn't it? So phospholipids again, like I said, these make up the probably complex lipids. And as you see here, you can see there's glycerol, which is an alcohol. Then you see there are two fatty acids there on the first hydroxyl, on the second hydroxyl with the glycerol. Then on the third, you see phosphoric acid, right? So you can see phosphoric acid there. And so what you are then getting is glycerophosphorcholine. So you get this wonderful structure. You've got the ester bonds there, and then you have the highly charged phosphate containing head group. So you see there's a phosphate, then that phosphate joins itself to choline. So you see the choline there, that's positively charged, and then you see the structure is going to be glycerophosphorcholine. Reason being glycerol because it's being formed from the alcohol glycerol. Phosphor because remember there is the phosphate, the phosphoric acid which had interacted. Then choline because that's the part there that has got the methyl groups there and the nitrogen which is positively charged. So they can ask you, what are the components of glycerophosphorcholine? So there is choline, there is phosphoric acid or phosphate, and then there will be the glycerol and then two uh, fatty acid chains. Okay, so you can see that that part on top, the phosphate and the glycerol part, it's highly charged. You can see there's a positive nitrogen there. Then, of course, these phosphates, when they lose that hydrogen, can be charged as well negatively. Whereas those two chains, fatty acids, which you are seeing down there, they are non-polar. Okay. So phospholipids are complex molecules made from fatty acids. I've explained that. Glycerol, I've explained that. Phosphate, I've explained that. And a large polar group, which in that case, as we saw, was choline. Okay, so that's important to take note of. So the phosphor, yeah. So choline is one of the most common amino alcohol used for this purpose. The phospholipid so formed is called glycerylphosphocholine. I've already explained that. So an important property of phospholipid is its polarity. The phosphocholine head is charged and is therefore soluble in polar solvents. Again, that's the positive charge that I was showing you on the nitrogen there. While the tail of two hydrocarbon chain is non-polar. Those were the two chains that I was showing you on the down part there. Now, phospholipids form the basis of all cellular membranes. Again, remember me mentioning the fact that lipids are very, very important in the formation of cellular membranes. So phospholipids form one of the largest classes of natural lipids and one of the most important. They are essential components of cell membranes, and phospholipids exist in many varieties depending on the fatty acids which have esterified or depending on the fatty acids which have actually uh, been added to the hydroxyl groups of the glycerol, which is the alcohol. In fact, the nature of fatty acids can greatly affect the chemical and physical properties of the phospholipids and the membrane that contain them. Remember, this is the fact that depending on whether a fatty acid is saturated or unsaturated, it can either have a high or low melting point. Of course, having a high melting point if it is saturated and a low melting point if it is unsaturated. In most cases, phospholipids have a saturated fatty acid at position 1 and unsaturated fatty acids at position 3 of the glycerol. So you get usually a saturated fatty acid at position number 1 and an unsaturated fatty acid at position 3 of the glycerol. Okay, so that's pretty much about that. So before we can start, yeah, so before we can just wind up and finish on lipids, so we can now talk about waxes. So you see when you get that alcohol there and stearic acid is just a fatty acid. So you get that alcohol, which is oleo, an alcohol, then you combine with a fatty acid, stearic acid, you get wax. Waxes are esters of long-chain alcohols with long-chain fatty acids. So remember, when we are talking about lipids, we are talking about glycerol. Glycerol, like you saw, it was only a three-carbon alcohol, isn't it? A three-carbon alcohol. But with waxes, these are made from what? These are esters of long-chain alcohols with long-chain fatty acids. Just look at the chain of that alcohol, oleo. It's long, eh? And look at also the fatty acid, stearic acid, it's long as well. But when we were talking about lipids in general, talking about those fats and everything, you saw that the glycerol was only how many? Three carbon atoms long. But here you see that the alcohol, the fatty acids are both long. So the resulting molecule can be viewed as having a weak polar head at the low non-polar tail. Fatty acids found in waxes are usually saturated, whereas the alcohols found in waxes may be saturated or unsaturated. So you can see there stearic acid is unsaturated. Oh, sorry, pardon me. It's saturated. It's saturated because it doesn't have any double bond. Whereas the alcohol there you see it's got a double bond, so it's unsaturated. However, the point that's being made is that usually, usually each the waxes, the fatty acids are going to be what? Saturated, whereas the alcohol can either be saturated or unsaturated. Now, this is very interesting because, and it makes sense, waxes are usually going to be solid it uh, it it in room temperature, right? At room temperature. That makes sense because what kind of fatty acids are usually solids at room temperature or have a high melting point, for instance? It's going to be the what? The saturated. So it makes sense because even the lipids that the saturated fatty acids are going to form, they are more likely to be what? To be solids. Huh? So it makes sense that waxes, which are usually solids, their fatty acids are usually going to be saturated, whereas the alcohols found in waxes can either be saturated or unsaturated. Waxes are highly insoluble due to the weak polar nature of the ester group. So again, remember, these are being formed from long chain alcohols, meaning even though the alcohol has a hydroxyl group, that's being weakened. Even though the fatty acid has got a polar group, a polar head, that's being weakened because the hydrocarbon chain is just way too long, so much that it's able to suppress the what? The effects of the polar parts, or in this case, the polar nature of the ester group. So that's why these ones, they have a very weak polar nature, and therefore they are highly insoluble in water. As a result, this class of molecules confers water repellent characteristics to animal skin, leaves of certain plants, and to birds' feathers. That's why you see that when you splash a chicken water, it rarely gets wet, you know. Sometimes the water will just run over the feathers. Even our skin, when you put water on your skin, only you realize that most of it will go down, and just small parts, okay, are going to remain. And also the leaves, it can be a heavy rain, but when you check the leaves on plants, you'll see that they only have small amounts of water because they are water repellent, because they tend to have wax on them. So the glossy surface of the polished apple results from a waxy coating. So when you look at apples, they tend to have that nice appearance. That's as a result of the waxy coating. So the next time we meet, okay, so we are done with lipids. We finished the topic. So next time we meet, we start proteins. So any questions?